All right. Well, hello, everybody. So I'm Mychaela Falconia. I'm the crazy GSM girl around here and presenting today on uh, the the intricacies of the TCH receiver interface. Yeah, basically what happens when either the base station or the mobile station receives on a speech traffic channel, and what kind of metadata flags we have to deal with, and some of the, you'll see the weird stuff. Uh, uh, So we start with the relatively simple part. I say relatively simple because this is documented. It's a lot easier to understand things that are documented in the specs versus things you have to reverse engineer. But this part is documented. And on the network side of GSM, where you have traditional E1 based transport between BTS and BSC, and then ultimately to the transcoder, to the TRAO. So this is the frame format you have. It's called a TRAO frame because this frame format is spoken between the BTS and the TRAO, transcoder and adapter unit, and it has different frame formats for the uplink versus downlink. So here we're talking about the uplink because we're talking about the BTS acting as a receiver. And there are two specs. There is one spec, OE.60 for full rate, and a different companion spec, OE.61 for half rate. So they're pretty much in parallel. So here, if you look at OE.60 for full rate traffic channels, for every 20 milliseconds, we have the appropriate number of frame payload bits. We have 260 bits for FR1 or 244 bits for EFR. Which are always there, and then you have the bad frame indicator bit. So if for some reason you never got you got fetch instead of traffic, or the mobile station was not transmitting because it was in a DTX pause, or really bad radio conditions, it just didn't get a good frame. Well, BTS still has to put out payload bits, but it also sets the BFI. It says a metadata bit. It says, this is a bad frame. Then you have the SIG classification. So for DTX purposes, the BTS receiver has to classify this frame that I just got. Should it be considered non-SID speech? Should it be considered a valid SID, or should it be considered an invalid SID? Because the TRAO on the other end of this E1 link will care about the specification. It has a spec prescribed algorithm for Rx TTX handler that acts on this classification. And then you have the time alignment flag, which I won't really be covering here because that one is pretty straightforward. The time alignment flag basically tells you this particular 20 millisecond frame, does it align with a particular position in the such multi-frame or not? Because the DTX specs say that there is one particular position in multiplex where you have to always transmit. And so RxTTX handler cares whether or not there was a correctly received frame or if there was a lost seed in the TAF position. So that's why you have the flag that says, I'm in that position. But that flag is just generated automatically by the BTS no matter what. So now if we look at the half rate, we have all of the same things that we have for full rate. Everything that we got in OE.60 is still there in OE.61. But now we have this one more flag, this unreliable frame indicator. So previously we just had the BFI, bad frame indicator. Now we also have unreliable frame indicator, which for half rate, the official rules for the XTX handler, it also says how, based on, it's basically a less severe error compared to BFI. So BFI says frame is totally bad. UFI says frame it is a suspect. Is basically what UFI means. And it's interesting, we'll get to that. I find it very interesting that this UFI bit exists only for the half rate codec, but does not exist for the full rate or enhanced full rate. So that's interesting. And so these are all the, questions which we'll get to. So this is network side. Now, it's also important to realize that what I cover here is these specs provide the same interface also in an abstract form. So you can think of it as I describe here, is there is an abstract form and there's a concrete form of the interface. So these three specs, 0631, 0641, 0681, they define the interface in an abstract manner, more of a conceptual thing. It's a conceptual, and it describes the semantics, and describes what the fundamental metadata flags are. It describes this is what the BFI flag is, and this is what the SID classification is, and this is what the TEF flag is. So it describes the flags in a general sense, but it does not tell you this is the order of transmission on an EVON line. That part, the order of transmission on the EVON line, that goes toward the other specs, OIDA 60, OIDA 61, which give you the same thing in a concrete form. This is how it looks on the network side. But the important part is that the abstract form exists on both sides, both network side and mobile side, whereas the other one, the trial frames, is only for the network. Now, I'm going to do a little trick here. See, I'm just going to very briefly switch to, oops, so I hit the wrong thing. Hit the wrong button here. Hit the wrong button. I was trying to hit the screen share button so I can show what it looks like in the spec. Yeah, this is what I meant to do. So yeah, this is what I was trying to show. So this figure right here, this is 06.41, or now as they call it 46.041 in 3GPP notation. But this this little diagram here, the one, and this one shows the extra UFI flags and information bits. Here it's 112, but for full rate it would be 260. For enhanced full rate it would be 244. And then this UFI would not be there in the full rate case, but the other ones are just exactly the same. So yeah, I just wanted to show what it actually looks like in the spec. So now I'm gonna turn this off. All right, so now we are back to my slide. Yeah, sorry for the little kind of confusion there. This, what I just showed you from the picture from the spec, that is the abstract interface. So from looking at that diagram in the spec, you can't tell in what order should the bits be transmitted or anything like that, but it tells you what the bits are, which is important. So now we have very interesting thing in the case of TI Calypso. So TI Calypso, which I covered in the earlier presentation, is just one particular implementation of the mobile side of GSM, which happens to be my favorite. So I've reverse engineered it quite a bit. And what I found interesting here is that they have implemented an interface internally that's conceptually similar to ABIS. So if you look on the network side, what I drew here, this ASCII art block diagram, it's pretty much the same thing as the picture that I showed from the spec. So you have the radio subsystem, which has all the channel decoding and whatnot. This is an EBTS. And this part, the speech decoder and the RxTTX handler directly adjacent to it, tightly coupled. These are in a trowel. So these are physically distant. The trowel would be collocated either with the BSC or even with the MSC. So this interface here, this ABS interface, and ultimately going to ATER in the case of MSC collocated trowel, this can span a significant geographical distance. So you have these trowel uplink frames in standardized spec-defined format, carrying all this information from this part to this part. They're very standardized. But now you look on the mobile side, inside the Calypso, well, here it's all inside the phone. And not only is it all inside the phone, it's all inside the single chip in the phone. And even inside the chip, it's inside the DSP block. So it really seems monolithic. So if it's all just inside the DSP, and even the ARM side of the Calypso doesn't really have to touch it. But it is sniffable. This is the fun part. Yeah, this is not really a Calypso presentation, but I'm going to gloss over the details. But there is a type of shared memory. It's called the API RAM that's shared between the DSP and the ARM part of the Calypso. It's basically owned by the DSP, but the ARM can access it. And it's a pretty small. I think it's like 8 kilowords there, from what I remember. And so in there, they have the dual buffered pages, and they have what's called the NDB page. So the NDB is the non-dual buffered page. That is the one that does not fully update on every TDMA frame. But they do have this little buffer inside this NDB page, which, even though it does not get updated on every TDMA frame, it does get updated on every 20 millisecond audio frame, which is basically 4 or 5 TDMA frames. And through obscure little bits of evidence here and there is how we as a community discovered the existence of this little buffer. And so in Osmocom BB for ages, there has been a facility to use an external, basically to not use the phone's built-in speaker and microphone, and use this external interface with codec frames. But even there, the first people who discovered it, they saw the buffer there, but it took I had to study it some more and figure out. We'll see. We'll get to the next slide, and you can actually see what this looks like. So here I am covering the simpler case of full rate. So of the three classic codecs, TCH FS is FR1 codec, TCH EFS enhanced full speech, that's the EFR codec, TCH HS is half rate speech. But here we look at the simplest one. So we already covered what it looks like on the network side. So on the network side, you have a TRAO UL frame, you have 260 bits of payload, and then you got these metadata bits that we already covered, the BFI and sys flags. But now, when we look at what happens inside TI Calypso, it's conceptually similar. The details are different, but same concept. Again, going back to the abstract versus concrete distinction. So we have all these status flags. So we have 3 words. The first 3 words are DSP status flags. And then the last 17 words, so 17 words equals 34 bytes, but the DSP is word oriented. The DSP does not have bytes. The smallest unit it can operate on is a 16-bit word. So they need 260 bits of FR1 payload, and they are stuffed into 17 DSP words. And the one big difference between ABIS on the network side versus what we see in the Calypso is the bit order. So on ABIS, the order of the payload bits in the frame is the natural order of codec parameters. So when you read the spec for each of the codecs, it describes the algorithm, how it does, the speech compression, the vocoder function, and it has these parameters, this parameter, this parameter. And so if you just take the parameters in a natural order as they are treated by the codec itself with a speech encoder and decoder, that's the bit order going across ABIS. But on a radio interface, the bits are reordered before they go into the channel encoder, which is convolutional coding and all that type of stuff. So, and in the case of the TI's DSP, in their internal buffer, they store bits in the channel code in bit order, which, it's an internal interface, internal to TI's implementation. They could use whatever bit order they wanted. So it's just, that's how they chose to do it. So they must have the reordering done on the speech encoder decoder side of the interface instead of the RSS side. But the interesting part, or at least the interesting part for this presentation, are all these status bits. So let's quickly go over the first 3 words. So the word 0 here, that's what I'm going to talk about, the status flags. Word 1 is still a mystery to me. This D_Mac, that's from a comment in the old TSM30 source, which does not appear in any of the later sources. So I'm mostly using the Lacosta source as my reference, but it's not there anymore, only in the ancient TSM30 version. I have no idea what it stands for. The ARM firmware does not use it. But empirically, the number in this word, basically the higher the quality, the larger the number. So as the quality goes down, this number also goes goes down. That's what I can tell. Now, and the third word, this one is used by the ARM firmware, and it's also intuitively obvious just from looking at the dumps, looking at the captures, that this is the number of bit errors detected by the convolutional decoder, and the ARM firmware uses this number in order to compute RX qual for measurement reports, which are prescribed by the spec. So that's how we know that word. But the word 0 is really the one I want to focus on here, because this is the one where all the flag bits are. And this one I mostly had to reverse engineer. There are a few hash defines in the TI, firmware source for ARM side. There are a few hash defines that give the meaning of some of the bits, but not all. And so the rest I had to just reverse engineer empirically. And this is the ones that I showed here are the ones that have a direct correspondence to A bits on the network side. So bit 2, I'm saying this is just like the C12 on ABIS. And these two, the C classification bits, just like the ones that, again, on Trau UL frames on ABIS. And then the other stuff, again, because this is not really a Calypso presentation, I didn't want to get into the other stuff. So that's in the case of the full rate. So here, elaborate a little bit. So when we have this BFI flag, so the BFI flag is defined in the abstract sense in, so 06.31 defines it for full rate, 06.81 defines the BFI for enhanced full rate. Same thing, same conceptual definition. So in the case of full rate, we know BFI is supposed to be set if we got fetch. And also there's a CRC3 done at the GSM 503 channel coding step. If that CRC3 is bad, you set BFI. That's obvious, non-controversial. Also, in the case of EFR, they have a CRC8, which only in EFR, not in the others. If that one is bad, again, you set BFI. So that's all very straightforward. So when any of these conditions are met, then on the network side, on ABIS, you have this Trau UL method EBIT12 gets set, and on the mobile side, in TI's DSP, you get bit 12. So, there's a slight complication there. In the case of EFR, if the problem is with the CRC8, they actually set a different bit in it, bit 9 instead of bit 2, and then the logic that follows deeper down in the DSP chain looks at both bits. But again, that's just an implementation detail of TI. That's not really, it does not change anything on the fundamental level. But then, in all cases, on both network side and mobile side, we have additional criteria. So not just these two criteria which we've covered, but we also have these unknown criteria here for BFI, which, I'm still quite interested in, because consider what happens in the case of DTX. So let's say you have DTXU in uplink or DTXD in the downlink, and you are at a transition point. You are at a point where the mobile or the network has just transmitted a silence frame, it just transmitted a SID frame, and then it's about to cut off the radio transmitter. Or vice versa, it's about to begin a talk spurt, about to turn on TX. Let's say if it's doing the mandatory SID position. So it's easiest to look at this in the case of the mandatory SID position. So let's say you are in a prolonged DTX pause, and every 480 milliseconds in the case of full rate, you have to transmit a SID update. So because it's GSM 503, what they call block diagonal interleaving, a single 20 millisecond frame, whether it be speech or SID, is interleaved across 8 bursts. 8, not 4. So even though 4 bursts would have been enough to carry the bit content, it's 8 bits and not 4 because it's block diagonal. I assume most people here know what block. I'm not going to go into too much detail. But now consider the impact of block diagonal interleaving on DTX starting and stopping. Is because you're going to have what I call the half block. So if you are required to transmit 8 bursts in order to transmit the mandatory set. Okay, so you put out the 8 bursts. In those 8 bursts, you have the block diagonal interleaved frame that you wanted to transmit. But then you also have a preceding half frame and a following half frame or half block. I don't know what to properly call it. But basically, you have in each of the bursts, the half of the bits belong to the other 20 millisecond frame position, the one where you don't want to transmit, but where you have to transmit those bursts. So this is from a transmitter point of view, it's real simple. From a transmitter point of view, the rest of the chain just runs continuously, and you just simply suppress the physical TX. On the radio side, you just don't turn on the PA. That's the easy part. But look at how this looks on the receiver. On the receiver, for the 20 millisecond frame position where the full frame was transmitted, everything will look good. But look what will happen in the directly preceding 20 millisecond position and in the directly following 20 millisecond position. In both of those traffic frame positions, the receiver will have 4 bursts out of 8. So out of the normal 8 bursts that it would have needed to do a regular decoding, it has only 4 bursts. Another 4 are missing. So the reason why this is very important for the BFI criteria is what happens typically in real life, at least, if the BTS and the mobile station are real close together, like in the lab setup, and the quality is otherwise really good. What will typically happen is the BTS or the mobile station, whichever, will still reconstruct the missing frame. So the frame that was supposed to be suppressed, for the one for which only 4 bursts arrived and not 8, from those 4 bursts alone, at least for the class 1 bits, it will reconstruct with half the bits missing. The convolutional decoder will reconstruct the frame. But at least all the official implementations, both the implementation in the Nokia inside BTS, thank you, Harold, thank you, Sarah, thank you to all the people who helped me acquire it. In that BTS, when it encounters this condition on the receiver, it sets the BFI flag in the output. Exact same thing in TI Calypso. In TI Calypso, it's actually weird because all the commercial networks that I have access to in my part of the world, they're all single carrier cells, so they don't actually do true DTXD. They can't. But I'm wondering if they're doing like a fake DTXD where they transmit dummy bursts in those burst positions that would otherwise be totally suppressed. But the end result is the same. To the mobile station receiver, it looks just as if they were doing true, honest to God, as they say, DTXD. And what the Calypso receives is in the frame that was meant to be transmitted, it receives the good SID frame, but then in the preceding position and the following position, it receives bits that look like a SID, but the BFI flag is set. So we know it sets the BFI flag when it gets this half block. It only gets 4 bursts out of 8. And actually, as I say, the logic, the standard prescribed or XTTX handler logic, the spec does not explicitly spell it out, but when you follow through the logic that is described, you will see that the logic depends on this behavior. So if this behavior was not there, if the BTS were to not set the BFI on those half blocks, then the comfort noise parameter interpolation logic in the RxTTX handler will get messed up. And that's actually what happens in the case of Sysmo BTS. I'm still thinking about the workaround because the Sysmo BTS PHY, unlike the Calypso PHY, unlike the PHY in the E1-based Nokia inside BTS, unlike all of those PHYs, the Sysmo BTS PHY, it just puts out the block of bits and does not have a BFI flag. So, if ordinarily, if it gets a totally bad frame, it just puts out nothing. It puts out completely suppressed payload. But in this case, empirically, it just puts out the bits, but there is no BFI. So I'm still thinking about the workaround. But in the proper implementation, this is how the BFI is supposed to be set. Okay, so we covered BFI. Now, the other thing is you have the seed classification. Again, on both the network side and mobile side, the TCH receiver has to classify each frame. Is this non-seed speech? Is it valid seed or is it invalid seed? And thankfully, for the full rate, both plain full rate and enhanced full rate, we have exact rules in the spec. So we don't have to go, reverse engineering things and bewildered head scratching. The spec says these are the thresholds. So if you have a perfectly pristine seed, 0-bit errors, it's valid seed. If you have just 1-bit error, so out of the 95 bits of seed code word, just 1 bit is wrong, that's also a valid seed. Between 2 and 15 bits wrong, invalid seed. 16 or more bits don't agree with seed classification, then we say it's non-seed. That's just a regular speech. So these rules are prescribed in the spec. And my experiments, of course, there's a saying, trust but verify. So I had to verify just for sanity, make sure that both the inside BTS and TI Calypso DSP, that they do in fact implement these rules exactly as spec says, and yes, they do. That's tested, confirmed. This is the way it's codified. So we have functions now in libosma core that implement this logic. I recently just now added the unit test for the EFR one, still have to do the one for the EFR. So that's all straightforward here with the full rate. But now we're going to move on to the half rate, where things get a lot messier. Yeah. So now we get to the half rate, and of course, practically half rate is like nowhere near as interesting, nowhere near as useful. But for the sake of completeness and intellectual curiosity and wanting to know, these are the new complications. So they added this UFI flag, unreliable frame indication, or indicator, whichever way you want to say it. So I've seen both ways of specs. Some specs say indication, other specs say indicator, and even though they're both ETSI specs, a lot like ETSI and 3GPP could make up their mind on which way they should say it. Just like transcoder and rate adapter versus transcoding rate adapting. Again, make up your mind. Or adapt or adaption or adaptation. Again, make up your mind. But both appear in the specs. So with this UFI flag, we know what's supposed to happen on the, I'll just go back a few slides. So I have this block diagram. Yes. So in this block diagram, when we add the UFI flag, the one that only exists in half rate, we know on this side, because this side right here, the RxTTX handler speech decoder, this is prescribed in the specs. The spec gives you a bit exact reference implementation, which everyone follows. So we know what happens here. It's this part that's murky. So again, I'll go back to the slide that we're supposed to be on. So here we have this new UFI flag, and we know exactly what the RxTTX handler is supposed to do with it. It has the prescribed logic. To be really pedantic, that logic is considered a non-normative example. So ETSI had a weird idea about what should be considered rigidly prescribed, which you have to implement exactly, versus what's only a non-normative example implementation. For some reason, in the case of all the codecs, the full rate, the enhanced full rate, half rate, with all of them, the ECU aspect, the way you do error concealment, they call that, they consider that non-normative. So they give you an example implementation, but you don't have to do exactly that way. Whereas other aspects, like for example, comfort noise, they tell you bit exact. You have to be this bit exact, otherwise you don't pass the conformance test. Interesting. So in the case of this UFI flag, technically speaking, for most purposes, this flag falls into the example implementation. part, the ECU part, basically. So the ECU cares about the UFI flag. Other than the ECU, the part that's normative, the one that you have to do, is when they classify for DTX purposes, like transition between DTX speech and DTX pause states. There they are BFI together with UFI, and that part is normative. That part you have to do, like they say. But the ECU part is considered an example. But in any case, what is normative, for example, either way, they give us C code. And when they give us C code, the easiest thing to do is just take it as is, even if it's not normative. But that's on our XTTX handler part and the speech decoder part. We still have no idea what we're supposed to do on the BTS. So if you are implementing a BTS and you are putting out TRAO UL frames of GSM 08.61, or let's say you're using my little specification, Themyscira Wireless Technical Specification TWTSO2, which does the exact same thing but over IP and RTP. And I've replicated all the same flags that exist on E1 ABIS. So what are the criteria for setting BFI? And what are the criteria for setting less severe UFI? Unfortunately, the spec does not tell us. It's silent. And now on the seed classification. On the seed classification, once again, there are three possibilities. So you can have a non-seed speech, you can have valid seed, you can have invalid seed, which our XTTX handler very much cares about. And so you have the same three classifications, but no more prescribed thresholds. So whereas in the case of full rate, the spec tells you this is how you shall do seed classification. These are the bit counting thresholds. But now they just give you an example solution. This is the actual word. This is how the spec is worded. So an example solution is in the C code, non-normative example. All right, well, let's look at that C code, shall we? And this is what the C code looks like. So the code drop that contains the C code is called GSM 06.06. So 6.06, you have a little tiny PDF spec that describes the code, and then you have the actual body of the C code. And so if you look at it just from a bird's eye view without drilling too much into the detail, you can break it down into these three parts. So the encoder it's normative. So in the case of the encoder, both the DTX mode and both the regular mode without DTX as well as the optional part with DTX, voice activity detector, all that, everything is normative. So every aspect of the speech encoder is bit exact normative. I mean, of course, you're free to re-implement the code however you want, but the input and output has to be bit exact match to the reference C code. And they give you this other companion spec 0607, gives you the test sequences. So for the encoder, they give you the linear PCM input that you feed to the encoder, and they give you what is supposed to be produced by the encoder on the output. And you have to match bit for bit to pass compliance tests. So the encoder is very straightforward. So now for the decoder, pretty much the same thing. Again, with the decoder, the only leeway they give you is that, as I mentioned before, the ECU portion of the decoder is considered to be a non-normative example, and it's not exercised by the test sequences. But everything else, every other part of the decoder, the regular decoder for speech frames, the RxTTX handler logic, and the comfort noise generation, all of that is bit exact prescribed. So again, they give you a test sequence, you have the frames that you feed to the input, and you have what's supposed to come out, and a better match or you don't pass the test. And then there is the third part of the reference source, which is this RAID, this residual error insertion device. And this part, that's where our C classifier is. So the interesting bit here is that this piece of code, this third portion, it is completely non-normative. It is non-normative. It is not covered by any of the test sequences. I mean, it was used in the process of generating test sequences. So the people who generate test sequences, they used this program. They took the code file, which is the output from the encoder. They passed it to RAID. They generated the DEC file, which is the input to the decoder. But the logic there is very straightforward, and most of this is not exercised. So, for example, this function that we're going to study in detail on the next slide, once, if you were to modify this function a little bit, it will not change this basic operation in any way. So it's really not exercised in any way by the normative tested path. And it is also, like I said, it's the least documented, most glossed over part, as you can see. So now let's see what it actually does. So this is the name of the function, and yeah, this code, GSM-166 code, it's pretty ugly. It uses Hungarian notation and camel case for function names. Such a pain to read. I mean, the EFR code is way better. The EFR code was probably developed by different people, I'm guessing. But yeah, the EFR code, that one actually has more Unix-like, Unix-style function naming scheme with underscores and all lowercase, none of this Hungarian notation stuff. But the half-rate codec is written like this: Hungarian notation, camel case. Yeah. But this function here, that's the one that does the RxC classification. And before we look at the actual code, we'll look at the comments. So first, we'll look at the arguments. What are the arguments going in? Okay, well, this part is obvious. So you have the bits that come in. Now, in a typical hardware or DSP implementation, the easiest place where you would put, the most natural place where you would put the SID detector would be right at the output of the channel decoder before you do the reordering. So, like I mentioned before, the bit order, the codec's natural bit order, and the bit order for the channel encoder, for all three codecs, they're different. So there's the reordering step. And here it's even messier for half rate, because with half rate, the reordering is mode dependent. It's different for the unvoiced mode versus voiced modes. But if you do the bit counting before the reordering, like if you look at the bit order used in the Calypso DSP, where they have a channel decoder bit order, then it will be real easy. But because this C program was written for this other interface, it was written with the expectation that every frame will be passed as broken down codec parameters. They use this interface. Okay, well, whatever. But then the second argument to the function is the hair raiser. So now, because previously, if you look at the C classification for full rate or enhanced full rate, all you have is just this portion. You would have the frame itself, the payload, and that's it. It's independent of error flags, independent of BFI, basically. BFI or no BFI, you still have the same classification. Well, now you have these three error flags. And even the comment even says that supposedly all three are just like it says, error flags generated by channel decoder. And then we have these other comments that say what each flag is. BFI, UFI, BCI. What is BCI? Because we know from the specs what BFI and UFI are, but what in the world is BCI? So this is where sort of the mystery began for me. When I first looked at this code over a year ago, what is this? What is this BCI flag? I mean, we don't even know what it stands for. Like bad channel indicator, maybe. But yeah, completely undocumented. What is this flag? And then we're going to see in a moment what it's actually used for. So this is the logic. So you have the case of BCI equals 0 and BCI equals 1. And you can see this threshold. So this is a threshold of BCI equals 0. This is a threshold of BCI equals 1. The rest of the logic is the same. And also notice how they only count class 1 bits for this check, but they count both class 1 and class 2 bits. So like I say, they give unequal weight, which makes sense. I mean, class 1 bits have the protection of the convolutional decoder, convolutional coding, whereas class 2 bits do not have convolutional coding protection. And in the case of FR1 and EFR, the seed field is all in class 1, so you don't have this complication. But the seed field of half rate, it uses all of the class 2 bits plus all the class 1 bits that are not used for comfort noise parameters. So basically, you have 33 bits of comfort noise parameters, which are all in class 1, and then all the other bits, including all of the class 2 bits, form the seed field. And so you do the bit counting, the function does the counts, how many class 1 bits are in error, then it counts how many class 1 or plus class 2 bits are in error. And then these are the thresholds. So the valid seed threshold is the same, but the threshold between, because this is invalid seed, this is non-seed speech. The threshold between these two changes with the BCI flag. But again, what is this BCI flag? What is this mystery here? And so, yeah, ever since I saw this code, I was so reluctant to just, incorporate it into libraries and whatnot, because what is this doing? What is this BCI flag? Is this at first? My first thought when I noticed this over a year ago, I thought, well, maybe this is some kind of leftover from an earlier draft version of the spec, which never made it into the final draft. And we'll find out the truth is actually a little different. But that's what it seemed to me at first, and that's why I was so reluctant to incorporate this code. And so once again, the TI Calypso comes to the rescue. So when I started using, and of course, there are no commercial networks that, at least in my part of the world, no commercial network will ever issue you HR1 codec. So all of my experiments with whereas in the case of FR, EFR, I started all of my Calypso experiments on commercial networks. But in the case of half rate, it's all just in the lab using either Sysmo BTS or more recently, the Nokia Inside BTS, using my own test network to generate test calls, configure the codec for half rate and see what Calypso receives. And so when I started doing these experiments a few months ago, I noticed this C007. Now, when I covered all of the classification, the status bits for full rate, half rate, for full rate, enhanced full rate, because this is not really a Calypso presentation. I didn't cover like every single bit in there. But typically, if I were in either FR or EFR case, I would be seeing one of these. So if I were to see a BFI frame in either full rate or EFR, which happens all the time, whether it be fetch or whatever other reason you have BFI frame, it will be the first word will be one of these two. So you have bit 2 set, then you will have bit 9 set that indicates the bad CRC8, which is only for EFR. But in the case of plain FR, it is always set as ignored. And then the C, the upper bits, those are Calypso isms, which are not really relevant for this presentation. So that's what you would see in full rate in the EFR case. But in the half rate, I'm starting seeing C007. So it really looks like instead of having a single bad error flag, it now has 3 bad error flags. And furthermore, I mentioned most of this is reverse engineered, but I got a little tiny bit of assistance from the TI's C source on the ARM side firmware, where they have a few hash defines for some of the bits. And so looking at those hash defines, there was actually a single hash define for UFI. So somewhere there's a hash define that basically says that bit 0 is UFI, which of course is only half rate. And I'm thinking to myself, okay, so if bit 2 is BFI, and according to the ARM side C source, even though the ARM side firmware never ever looks at this bit, so that hash define is just there, it's purely superfluous, it's never actually used. But suppose bit 0 is UFI. Okay, well then what is bit 1? And so at that point I will become full of hope. Could it possibly be that elusive BCI flag I've been looking for? And basically the answer is yes. So, yeah, as I'm going to cover on the next slide, I used, in order to see all of these error flags in action, I had to come up with some way to create different levels of error condition. So I was thinking, okay, well, how can I create receiver conditions in the Calypso DSP where it will basically gradually go from perfectly good reception to really bad reception with lots of bit errors? How would I do that? And then I got the idea, oh, I can just use my CMU 200 instrument. So I'll cover on the next slide how I did that. But yeah, using the CMU 200 instrument, I did a few tests where I basically simulated bad radio conditions that start out as good and then gradually get worse. And by doing that, I was able to see the different error severity conditions. And so I could actually see these bits being set separately. Because if you don't do this, if you just have a lab setup where in your own lab, you have your BTS and you have a mobile station, and they're right next to each other, or, at least within the same apartment, same house, whatever, typically you're going to have 100% perfect reception all the time. And so the only BFIs you're going to see are not going to be a result of bad reception. They're going to be a result of either DTX in action or as a result of fetch stealing. Those will be the only reasons you're ever going to see BFI. So if I wanted to see the other error conditions, if I wanted to see UFI without the EFR, without BFI, and want to see BCI, I had to basically create more, less severe errors. And so, yes, now we know that these 3 bits, that all 3 flags are there. And also these bits 4 and 3, they have the turn receive classification, just like for the full rate. Just like for the full rate, you had the classification of seed, same thing here. And what's really awesome is I was able to verify that the seed classification is just like an ETC code. Now, this is important because it's a non-normative example. Remember, in the case of half rate, ETC did not say you have to do it like this. They just give you an example solution. So TI could have easily done something different, but no. What TI's DSP has done here, their logic exactly matches this example version from ETSI, including the effect of this bit. So that's what clued me in to really confirm that, yes, bit 1 really is BCI, because in the captures that I obtained with all the induced errors from the CMU 200, I could see that the threshold, looking at different bit patterns that just randomly occur, in the case of all those errors, I could see that it would use the threshold of 11 when this bit is clear, and when bit is set, it will use a threshold of 16 between seed 0 and seed 1 classification. And then the other threshold, the threshold for seed 1 to seed 2, that one is only based on the class 1 bits, and again, just like in ETSI's version. So yes, we have an actual commercial vendor that produced ginormous number of units of this on the mobile side, where they actually use the logic from that ETSI reference version. Yes. So let's see. Here I describe my CMU 200 experiment, what I did. So I used my own F3B, which was just more convenient, because if I were to use a regular phone, they'll have the built-in antenna, and you have to do all kinds of hacks to bypass the internal antenna. But F3B is a dev board that has an SMA connector for the antenna interface. So just disconnect the antenna and connect a coaxial cable from the CMU 200 directly to the F3B, and now you've got a self-contained network setup. And so the CMU200, it's a mobile tester. It has high level and low level test mode. So at the low level, it can just do all your basic RF tests, like a spectrum analyzer and whatnot, or a signal generator, spectrum analyzer, all the low level RF tests. But at the highest level, you can actually emulate the GSM network. Of course, the software inside CMU200 is proprietary, so the number of things you can do on a simulated GSM network with this instrument is much more limited compared to SMACOM-based test network. But it's just different tools for different applications, because the advantages you get with the CMU200 that you can't really do can easily do with a BTS is because it's an RF test instrument. You can dial down the TX power level. So I can start out, I can have downlink at healthy minus 80 dBm or something, and then I can just turn it down very slowly until I eventually hit radio link failure, and I can catch everything in between. Yeah, so this is what I did, and that's how we know the hierarchy. That's how we know that BCI is the least severe of the three errors, because one observation I immediately made about Calypso DSP is the Calypso DSP will always set the more severe and the less severe error flags. So if the DSP sets BFI, if BFI is set, then the other two will also be set. That's why you see a 7 in that last hex digit, because all three flags are set. So then if it was set BFI, well, if it said BFI, it would also set BCI. So you will see a 3 in that last hex digit, because both BCI and UFI are set. And if it sets just BCI, well, because BCI is bit 1, you're going to see a 2 in the last hexadecimal digit. And then, of course, if there are no errors, if you have perfect reception, you're going to see a 0 as the last hex digit. So these are the only 4 possibilities that can ever occur in the last 3 bits. So we know, so we know what the severity hierarchy is, and this is also when as I would turn down the downlink power level. At first, I would start seeing BCIs, then I'll start seeing BCI plus UFI, and eventually start seeing all 3 up to BFI. So that's how we know the error severity. Now, the unfortunate part, the part that still bites, is that we don't know the criteria. So I thought, okay, could it be some kind of threshold based on how many convolutional decoder bit errors? Nope, not the case, because for every hypothesis I had regarding the decoder bit error count, I could find counterexamples, and I've posted. The captures that I've posted from the experiment, they are posted in the retro GSM wiki in Redmine. Yeah, I posted all the files there, so you can see for yourselves that. It could be based on the DMAC field, but that one's completely documented, so we don't know anything about that. So that's the unfortunate part. No criteria are known. What are the criteria for setting these different error severities? No idea. All right. So this is the other part. We're almost done. This part comes from ETSI. So in the spec, in our 641 spec, they have this very curious wording, and it's very obvious that this wording in the spec refers to this portion in the C code. I mean, what else could possibly? Of course, it refers to this. And I've added some of the comments. I added these. Basically, this is otherwise a copy and paste in the original code, but I shrunk it a little bit and I added the comments. So if BCI is set, then you have the threshold logic that we already covered in the previous slide. And then we have this gem. If the number of bit errors in the, what I mean by bit errors, number of bits in the seed field which do not match the seed code word, both class 1 plus class 2 bits, if it's greater than or equal to 16 and less than or equal to 25. So here, because it's greater than or equal than 16, at this point we are in a non-seed classification. This logic that's up here has already decided that this is not that this is a non-seed frame. So now we see all of this, and we go, okay, well, if the bit pattern essentially meets these criteria, then BCI gets turned into BFI. So essentially, the lowest error severity magically transforms into the highest error severity. That's the effect of what this code would do if you were to actually apply it. And so, obvious question, why? Another thing I found curious is in TI's case, this logic is not applied. Now, I have to always, put a disclaimer. So, all of the experiments that I did in Calypso, I was using the final revision of Calypso Silicon, which is DSP RAM 3606. I have not tried this on earlier Calypso Silicon versions. I mean, which I do have access to. It's something maybe later I will test out of curiosity, but time is finite, so didn't get around to doing that. And I've also tested with this patch version. So because I'm using official code from TI, I'm using the latest final official patch that they produced for this DSP ROM. And so at least with this combination, this logic is omitted. TI's DSP is not doing this weirdness. Because it becomes a question of curiosity. Would it, if I were to use an older DSP RAM, or if I were to, an older Calypso board with an earlier chip, or if I were to run without the patch, was the logic there? Did they take it out because they thought it was just a bad idea? I don't know, or maybe they took it out. Maybe from the beginning said, no, we don't want this logic. Maybe they took it out. Right at the beginning, we don't know. At least right now, we don't know. But that's a point of curiosity, nonetheless. So, yeah, and then this was my original title for this presentation was TCH Rx error flags. Why did Etsy lie by omission? It may be a little bit too strong of a statement, lie by omission, but it's really strange when you have a standards body like ETSI publishing GSM specs and publishing reference C sources. And essentially, the reference C source has a status of a spec. It's a spec written in C instead of English, but it's still a spec in a way. And they have these references to the BCI flag that's not actually documented anywhere. They even say what BCI stands for. I mean, it seems like a lie of omission to me. And so I was wondering, why did the Etsy screw up so badly? And so here it's just some of my musings, some of my hypotheses. So the first thought I have on this topic is why is the BCI flag omitted from the trial UL frame? So when we look at the TI Calypso DSP, we see all three flags. But on the network side, when we look at the ABS interface from the BTS ultimately going to the trial, the BCI flag is not there. It's just BFI and UFI. So, but here we can actually, it's easy to understand, at least with additional thought, maybe not easy right away, but after some thought, we can see why it's omitted there. Because if the only effect of the BCI flag, if it affects the Rx classification block, if it affects the SID detector, and then the SID detector can also sometimes do this weird upgrade to BFI, but once the Rx SID detector has done its job, then the BCI flag has no more effect. And in particular, it has no direct effect on the spec-defined Rx DTX handler, the part that sits in a trowel. So if the logic in the trowel is not affected in any way, at least not directly, only indirectly, but directly it's never affected by the BCI flag, then we can see how they omitted this flag from the trowel UL frame format, which of course in practically contributes to it becoming more obscure and less understood. But that's how it is. Then, okay, well, how did it come about? Where did this flag even come from? How did, and why did the ETSI come up with such a complicated scheme? Why three different error flags? Because even if it wasn't for the BCI, even if BCI wasn't there, there's still the fact that we have the UFI flag, the unreliable frame indicator, that only exists for half rate. It does not exist in full rate and the has full rate. Well, why? Why not? If it's a useful thing to have, why not have it in others, right? So it makes me wonder how all this came about. And so this is pure speculation. I'm wondering. I mean, I've read somewhere, like history books, wiki pages, whatnot, Wikipedia, is that this codec, the half rate codec, was developed by Motorola. And furthermore, it looks like there was some kind of like a competition process. So there were multiple proposals. So multiple companies put forth their proposals for the half rate codec. And then ultimately, Motorola won the standardization process. And the other ones, well, the other candidates basically go to, let's say, to the dustbin of history, right? So I'm thinking, all right, well, if the companies who were there, so the Motorola and other companies who proposed these candidate codecs for consideration, I mean, they have pretty high stakes, I would think, because they wanted to win the standard. Because if they don't win the standard, if the standards committee adopts someone else's proposal, well, then all the work they did creating the codec, all that just goes to the trash. And so I'm wondering if, as part of the bidding process, maybe I don't know if bidding is the right term, but as part of this competition for whose codec proposal will be adopted as standard, what if they did more than just the codec itself? What if they also worked out for the codec proposal, if they worked out the channel coding scheme and also did real simulations? I'm just wondering, like in my day job dealing with terrestrial microwave, there are all these channel models for, where we add the, what is it called? The AWGN, additive white Gaussian noise, is being added to the channel model. And it's all done in software because, hardware is expensive. ASICs are super expensive, gigahertz, microwave, whatever. And so before people spend the money to build an ASIC, everything's going to be prototyped in software, like pure software simulation of the entire process from the transmitter all the way to the receiver. The behavior of the RF channel is going to be purely simulated in software. So I'm wondering if Motorola did the same thing with their half rate codec proposal. If they, if they created, the complete design for the channel coding, decoding, taking the already existing one for full rate, adapting for half rate, but also, what if they were the ones who introduced those UFI and BCI error flags as part of their design process, and they were playing around with channel models, AWGN or whatever they use to simulate errors? I don't know if this is what happened. We might never know, but it's just speculation that maybe that's how it all came about. And if indeed it all came about in this manner, well, maybe ETSI then felt that BCI did not deserve, so to speak, to be included in the standard because it's a private detail. Because if you think about it, it's not essential for interoperation. So if because the standards are concerned with interoperable interfaces. So if the interoperable interface from the BTS to the TRAO only needs to include the BFI, UFI, and the C classification, and on the mobile side, conceptual equivalent of that, and also, and of course, on the air interface, the interoperable air interface, there only the transmitter has to be specified, the details of the receivers, anyone is free to improve however they want. So maybe Etsy said, well, okay, the BCI, I think, has a private detail of Motorola's implementation. Maybe, I don't know. And then, okay, well, why TI Calypso got the exact same thing? Well, maybe TI just licensed the whole thing from Motorola. I don't know. That's all I guess. So everything on this slide is speculation. But even if all of these speculations are still true, even if all is 100% correct, still in my mind it feels kind of wrong for ETSI to not document it in any way whatsoever, because they gave this C code. Like, there is the reference C code. They knew when they published the C code, people are going to be looking at the C code, and it makes use of a flag that's completely undocumented. I think that's kind of bad on Etsy's part. And this is our final slide, the relevance for SMACOM. So this kind of brings us back to where it all started, because I started going down this rabbit hole a little over a year ago when I first implemented the C classifiers for full rate and the FR EFR. Because again, here, in my own Timescaler wireless network, I don't use half rate. I use full rate, of course. But I wanted a really, really good, rock solid implementation of every detail for full rate and EFR. So I implemented early on the C classifiers for full rate and EFR, which were easy, and the spec says exactly what the thresholds are, so I just implemented the spec. And for the sake of completeness, I wanted to do the same thing for half rate, because SMACOM supports all the Cisco BTS5 supports all three codecs plus AMR and other stuff. And throughout, just looking at the code base, looking at OSMO-BTS code paths, you have all basically the three non-AMR codecs, FR, HR, EFR. All three of these classic codecs, they're all handled together, following pretty much the same code path everywhere in SMACOM, and also everywhere, even in my own Timescaler libraries. The stuff that I'm doing, like with transcoding G.711 media gateway, there's no reason to treat them any different. So half rate is sort of grouped together with full rate and EFR in this case. So I wanted to have a C classification function, but as soon as I started looking at it over a year ago, like, well, there are no rules in the spec, and we have the example code in that, in C code from Etsy, but it's this weird thing with BCI. What the hell do we do with it? But now that we finally understand, what the BCI flag is, and now that we see that this example code, now that we have evidence that this function right here from Etsy is in fact implemented in real life in TI Calypso on the mobile side, well, that gave me the confidence boost to propose this as a Gerrit submission for libasma core, which has now been merged. So now this function, Osmo HRC classifier and libasma core, libasma codec, it implements the same logic. So, of course, I couldn't copy the code from ETSI, and I didn't need to. I implemented it myself. The code implementation is my own original, and the frame format is different, because in Etsy's version, the frame format they use is this broken down frame of 18 parameters, whereas in the SMACOM universe, what we really need is the TS101.318 format, or anything that's built on top of it. So this function, I designed it to use TS101.318 14-byte frame format. It's still not as efficient as it would have been otherwise. Like the most proper way how you would do it in a hardware or DSP implementation is you would couple this logic directly to the channel decoder before you do the bit reordering. But that would not really work well on the SMACOM, because at least I still want to support SysMo-BTS hardware, SysMo-BTS PHY as much as possible. And that PHY already gives you the RTP frame. You don't get access to the raw 503 channel decoder guts. So I just had to do it like this. So we have the function. We still don't, of course, the downsides, these two bullet points, these are still the remaining downsides. We don't have any idea what the criteria, how to set these bits. So far now, we'll just pass false for the BCI and not set UFI. And that pretty much brings me to completion. So now we do Q&A.